Okay, in the third part of chapter 7, we will introduce Smith chart applications, which includes the single star matching technique, double star matching technique, and the transformation across discontinuity. And in section 7.6, we will discuss about the loss in the transmission line. What happens and what are the impacts of lossy transmission line toward the reflection coefficient and impedance change in the transmission line. In particular, we are more interested about the power flow because the purpose of a transmission line is to deliver signal or deliver energy. In terms of energy or signal delivery, of course, we want to deliver as much as possible of the power of the energy available. All right, so in this section, we will consider a few examples of graphical solution on transmission line matching problem using the Smith chart. And to get hand-on experience on the procedure of Smith chart, a transmission line design software based on Smith chart is introduced. Well, I'm not sure did I put the software on the Moodle. I will check this out during the break, okay, during the lecture breaks, and you can do that by yourself on your own computer. And I will also do a few demos once we introduce the procedure for single stop and double stop matching. All right, and here's an example that we need to perform matching, perform impedance matching. This example is antenna, okay? We know that antenna is, well, it can be regarded as a a means of transformer because the general characteristic impedance of most transmitter or transceiving devices is what? 50 ohm, okay? It's 50 ohm. As I already told you many times, that 50 ohm is not a resistance within the transmission line, right? What is the true meaning of 50 ohm? Well, it happens to be the ratio of signal voltage over signal current in the transmission line. So the voltage will be 50 times larger than the current in the transmission line. And we know that for electromagnetic waves propagating in the space, the characteristic impedance, not characteristic impedance, I'm sorry, the intrinsic impedance, which is defined in terms of the ratio of what? Electrical field over magnetic field is what? Is 377 ohm. It's 377, okay? And if you do the division of electrical field over magnetic field, the unit happens to be ohm as well. So, so for waves propagating in the space, you can have the so-called intrinsic impedance to characterize the ratio between electric and magnetic field. Therefore, from this perspective, the antenna can be regarded as a transformer that bridges the difference between a 50 ohm system and 377 ohm transmission line system. Okay, so from this perspective, the antenna can be regarded as a transformer. However, you can characterize the role of an antenna from other perspective. For example, not for example, yeah. Well, yeah, for me, I would like to think of it as a structure to help you change the format of energy. Okay, like the example I always do. So you change airflow into acoustic wave. So from transceivers to waves propagating in the space, the antenna, which is in general a resonance structure, convert voltage and current signal into electric and magnetic field in the space. Okay, so from this perspective, it can be regarded as a converter, okay? Conversion, converting device, converting between different form of energy, different form of energy. But anyway, if you regard it as a transformer, then it's bridging the difference between transmission line characteristic impedance and intrinsic impedance in the space. But sometimes it may be difficult to directly convert the input impedance of the antenna, or to have the input impedance of antenna as 50 ohm. Sometimes it's difficult. One example, let me give you one example. E-tag, you know that? E-tag, okay? So about 6 or 7 years ago, well, about 10 years ago, okay, we started using, well, the first generation of electronically toll system is conducted via infrared. You know that? You need to install a small phone-sized device on your vehicle. So the first generation one is actually an infrared system. But the second generation one is the so-called RFID, radio frequency identification, okay? The frequency, what is the frequency? The frequency is, well, 950 megahertz. Well, somewhere around that. So we usually refer it as 950 megahertz. What is the wavelength of this signal? Wavelength. 33 centimeter. Yeah, why? Because 1 gigahertz is 30 centimeter, right? So for 950 megahertz, about 33 centimeter. So to come up with effective antenna, the size of antenna must be at least a quarter wavelength large. It's kind of a rule of thumb, a design rule of thumb for antenna design. If you want to design an antenna that has radiation efficiency greater than 90% or 80%, the size matters. The size must be at least a quarter wavelength large. So from this perspective, the size of the E-tag should be in the order of nearly 10 centimeters. However, it seems that the E-tag's antenna size is somewhat smaller than that, okay? And another important perspective about the E-tag is it has no battery. It contains active elements, but it has no battery. How? Because the E-tag antenna, well, if you have taken a close look at it, the E-tag antenna is connected to a tiny little integrated circuit. That's the integrated circuit of E-tag, which is smaller than 2 millimeter or something like that. So it's referred as RFIC, radio frequency integrated circuit. And it's relatively small, its structure is relatively simple, so that it consumes very little power. But it comes with no battery. So how it works? Well, when you enter the region for the ETC gate, on the highway, the RFID reader will provide electromagnetic wave around this frequency, and the wave will impinge upon the RFIC via the E-tag antenna. And this wave will wake up the IC, say, come on, wake up. What is your number? So what E-tag do is report its serial number. So every E-tag comes with distinctive number. And what the IC do is, when it is wake up, if the RF signal charge up the RFIC provides enough power to charge up the IC will generate a series of modulated signal which contains the information of its serial number. So the operation is relatively simple. But to wake up the RFIC, you need to provide enough power. Well, for RFID radio frequency identification application, the law restricts the maximum power of it as 1 watt, which is not a large number. And it turns out, at a distance of a few meters, this power level is not enough to charge up the E-tag. So therefore, the company who is in charge of this business apply a license or a specialized appeal to, come on, let's bump up the power. So eventually, the power radiated by the RFID reader is about 5 watts, 4 or 5 watts. And it's enough to wake up a E-tag IC at a distance of 10 to 20 meters, okay? And now, well, actually, for the E-tag company, it comes with 2 systems. One system is E-tag. The other system is what? The optical system. Similar, now when we went into the parking, most of the parking lots now come with the optical system to differentiate the number of your license plate, right? Yeah. Well, it's relatively convenient, yeah. But the E-tag now is kind of a backup plan. So with the fused result from optical system and RFID system, you can have a better accuracy in determining the license plate number on the highway. Oh well, 我真正要讲的是啥 ？OK， well, because the E-tag RFIC is relatively small, relatively simple, it cannot afford a matching circuit. So, in fact, the input impedance of RFIC is something like 30 plus J140 something. So actually, for most most RFID IC, its input impedance is not 50. It's not 50. So it's the antenna's designer's job to match this impedance. So it's not 50. Okay. But well, it's turned out it's not that difficult. It's not a very difficult job to match the output impedance of the E-tag IC, right? So this is kind of an example of non-50 ohm transmission system, transceiver system. Usually, you can, if the input impedance of antenna is not 50 ohm, you can apply a matching network. So in the follow-up slides, we will introduce two types of impedance matching network. And the design of a matching network can be done through the Smith chart. Imagine that about 25 years ago, there is no personal computer. There's no personal computer. How do you proceed for the design of impedance matching? So the invention of the Smith chart is really helpful. You can do the calculation on the paper without actually using the computer or a calculator. Okay. So I will skip up the software part now, and we will do that later about the software. Well, but a few things that you should remind yourself. On the Smith chart, the complete circle is the so-called equal resistance, the real part of the impedance. For those lines that are not making circles are the equal reactance one, are the equal reactance circle. The red circles on the plot are impedance, which is the so-called Z chart. And you note that there are also green circles. Okay, so they are invented to help you do Z to Y or Y to Z transform without taking the jump. Okay, you can you can do your follow-up procedures by following the green line instead of the red line, so that you are entering the Y chart. All right. So the Y circle, the green circles are plotted as an image of the red circles. It simply rotates 180 degrees. You can plot those green circles. But one thing you need to remember carefully is on the Z chart, the short is located on the left. Why? Because the reflection coefficient here is -1. It happens to be the reflection coefficient of a transmission line system connecting to a short. On the right-hand side, if you are looking at a Z chart, it represents an open termination. On the other hand, if you are looking on a Y chart, then the open and short circuit position will be interchanged. It will be interchanged. All right. We will introduce the single stop matching design, which is done by connecting a stop, which can be short stop or an open stop. Okay. In the textbook, in section 7.4, we have an example of connecting a short stop. But a short stop of a quarter wavelength will exhibit an input impedance of infinity. So a quarter wavelength long short terminated stop is equivalent as an open stop with zero length. On the other hand, an open stop of a quarter wavelength long is equal to a short stop. So you are not necessary to use only short stop or open stop. Well, both shall do for the single stop matching technique. All right. Here are some remarks about admittance. For the admittance part, the y equals to j omega c and equals to 1 over j omega l. So what is the purpose of this stop? The stop length is used to adjust the magnitude of the susceptance provided by the stop. And here are some illustration about the software operation, which I will do that later. And in this example, suppose we have load of 100 minus 50J. What is the normalized impedance of this thing? 2 minus 1J, right? Now just divided by characteristic impedance. Well, let's talk a little bit about operation of the software. So you type the value of the input impedance in this part, and then the reflection coefficient will appear on the Smith chart, showing the value of the input impedance you enter. The second thing is connecting the load with a transmission line, with a piece of transmission line. Note that we are doing the Smith chart, from right to left, from the very end of the transmission line termination toward the generator. Therefore, the locus of the characteristic impedance shall rotate clockwise on the Smith chart. So, and press this button, a circle appears on the Smith chart. What is the name of this circle? Constant SWR circle, okay? You can move your position with your mouse on the circle. Well, to determine the length or the position you are interested to. For this example, for this single stop matching problem, our objective is to reach the unique conductance circle, which is drawn as solid line in this figure. So the blue circle is the unique conductance circle on the Y chart. So you are supposed to have two solutions, which are the intersection of the unique conductance circle and your constant SWR circle. So you see the two butts, okay, two cross mark on the plot is the place that you should connect your stops, okay? Why? Because a shunt stop with open or short termination can provide only the susceptance, the reactance, the susceptance. But it can provide any value of a susceptance so that once you connect the stop, the input impedance, the reflection coefficient will move along the uniconductance circle. 好，这边来一个重点了。在这个地方，在这个叉叉的地方或上一个叉叉的地方，只要你接上一个 stop 的话，会发生什么事情？好，因为原本的路径在这边，它所看到的是一个，我要 G 等于1嘛，然后 B 等于，像这边看起来是负0.2之类的。好，他会看到一个 G 等于1值，还有看到一个不等于0的 B 值。好，那你在这个地方，假如说他看到的是负0.4B 好了，哦，假设负0.4B 好了。假设我接上一个并联上一个 stop， 然后它提供的是正0.4B， 那你所看到的有效的那个 admittance 是不是1减 0.4B 加上1减 0.4J 加上 0.4J 等于1，所以它就会沿着 constant G circle 倒回去到这个地方。好，所以在 Smith chart 上面的操作，当大部分假如你是在传输线上面左右移动的话，你是在 constant SWR circle 上转。但假如你在某一个地方并联一个 stop， 注意哦，因为是并联的动作，所以你应该要换到 Y chart 比较方便。而这个并联的动作，因为你要接上的，以我们现在的show stop 的例子来讲的话，因为你只调整它的 B 值，没有调整它的 G 值，所以它的新的位置会在那个 constant G circle 上面转移动。好，那比如说这个点本来它的读起来的 Y 值是1减 0.4J， 你给它加 0.4J， 那个 J 的部分就没了嘛，所以它就回到这边。但本来是1减 0.4J， 你再给它并上一个负 0.2J 的话，它会跑到哪里去？它会变多少？它会变1减 0.6J， 所以它会跑到，它事实上也是往回跑，它会往回跑，但跑不够了，跑不够了，往上去跑一点点，所以它还是没有达到 matching， 好，所以本来是1减 J 0.4嘛，所以假如你加上一个 J 0.4的话，当然就虚部就抵消了。你假如是接负的话呢，那就会变1减 J 0.8。注意哦，它会怎么转？事实上它还会往这边转，事实上它还是会往这边转。那个转法会有点有趣我不知道怎么讲，可能等一下那个看软体的操作的时候会比较清楚一点。All right. So at that point, well, the one convenience that you can have with this software is it always shows you the actual impedance. Even though now you are located on the Y chart, it still shows you the impedance. So you can see that even though point 2 is located on the constant G circle, the resistance is not unit resistant. It's unit conductance G equal to 1, but R is not equal to 1. Okay. All right. So in this toolbox, you can connect a shunt stop or a series stop. Okay. So you can actually perform quarter wavelength transformer by aiding a aiding a transmission line in series. Okay, but for this case, you are aiding a transmission line in shunt, 并联, and the line characteristic impedance can be characterized as 15 ohm, and the stop type can be specified as a shorted stop or an open stop. So once you connect, and well, in this case I place an open stop, well, but that doesn't matter, okay? So it adds up a different value of susceptance. So the point is actually moved this way, now in this way. But eventually you can find out with shunt stop or open shunt stop of 0.375 wavelengths, you will reach the matched point. Because the open stop, the susceptance provided in an open stop is a positive value at the beginning. Okay. Well, if you use a short stop, then the locus moving from 0.2 to 0.3 is counterclockwise, because a short stop will provide a small piece of short terminated stop will provide you negative susceptance. Wow. All right. So here's an example. Well, we will do that. Example 7.5. So in this example, we have a 50 ohm transmission line. The load is 30 minus 40J. So what is the normalized impedance? 0.6 minus 0.8J, right? And it's located at where? Oh, I'm sorry. 0.6减0.8吗？对啊，0.6减0.8。对，我怎么觉得怪怪的？哦，不是这个图了，不是这个图。对，好了，这边我只要告诉你讲，就是说那个 unit conductance circle 本来是在这里了，但是在反转的 Smith chart 的话，它会跑到另外一边去。所以目标是让导纳值落在 unit conductance circle， 然后用 stop 来去抵消它。所以刚刚那一题那个点，so the normalized admittance is 0.6， normalized impedance is 0.6 minus J.8. And because we are working with single stop matching, so the first step is to find the admittance of 0.8, which is located on the opposite of the unit of the constant SWR circle. And if you are taking the inverse of 0.6 minus J.8, it happens to 0.6 plus J.8. No, it's well, it's actually a straight line over here. Yeah. Well, let's have a break. Okay. So for example 7.5, the impedance at the determination is 30 minus 40J. So the normalized input impedance is 0.6 minus J.8. That is 0.8 on this figure. So the first thing, because we are going to do single stop matching, so it's more convenient to work on the Y chart. So we need to convert the impedance of 0.8 into admittance of 0.8, YA. And we can do that by taking the opposite position of the SWR, constant SWR circle, that is point B. If you do the 1 divided by 0.6 minus J.8 manually, you will find out the corresponding value for point B is actually 0.6 plus J 0.8，好，所以0.6减0.8的0.8 J 的导数其实就0.6加0.8 J，好。Alright, so once we reach point B, we can starting moving along the constant SWR circle. Our objective to have an intersection with the constant conductance circle, that is the G equals to 1 circle. So as this plot, on this plot you can see that there you have two opportunities to make intersection with the constant G, the unit G circle. They are position C and position F, right? So you actually have two solutions. So the first solution can be found by moving point B to point C. So we know we move along the transmission line. We move along the transmission line from B to C. And what is the corresponding lenses for moving from B to C? Well, again, you check up the markers on the outermost circles. For point C, the marker reads 0.1665. And on point C, the marker reads 0.125. So the difference is 0.0415 lambda. So this is the distance required to move from the termination to unit conductance circle, to unit conductance circle. So for point C is resist, and for point B is 0.125. So actually point A and B are located on the on the y-axis. That is 0, where the reflection coefficient is purely imaginary on that line. Well, anyhow, the distance required for move from B to C is, well, it's a small section. And the next thing that is important is the admittance on point C. What is the admittance of point C? YC 会等于多少? Well, one thing for sure is the real part is 1. How about the imaginary part? Because C is on the upper half of the plane, so it's a positive number. What is it? Okay, it's 1.16. Okay, you should know that the value of susceptance of point C is 3 from this line. Going all the way up, you found that it's slightly greater than 1. Okay? So it's 1.16. So from the perspective of the transmission line, we are moving from the load, ZR, with a small distance of 0.0415 wavelengths. And at this point, YC equals to this. If we want to achieve goal of unit admittance, what is the required size, required number for the susceptance provided with the shortstop? 你的 show stop 应该提供多少的 subsectance？ 负的 1.16 嘛，对不对？负的 1.16， 所以负的 1.16 要从哪里找？ Well, where's the location of zero length shortstop? Where's the admittance of a zero length shortstop? What is the impedance of a zero length shortstop? 0. So what is the admittance? Infinity. So for a shortstop with zero length, where is its location? Well, over here, right? So if you have a zero length shortstop, its admittance is infinity, so it happens to be on the right-hand side of the Smith chart. So point D is actually the admittance for zero length shortstop. How about shortstop with certain length? Well, if you take a look at your Smith chart, beginning from point D, you will read some small number or large number. Well, large numbers. 100啊，200、100，然后越来越小。Those numbers are keep getting smaller and smaller on the bottom half of the Smith chart. And it will reach to -1 at the bottom and become a number smaller than -1. 不是 smaller than -1, with size smaller than 1. 负0.8、负0.6、负0.多到对面的时候是等于多少？0嘛。到对面是0，所以一个长度为0的 shortstop， 它的电纳值为无限大。当它的长度开始变大的时候，它的电纳值就越来越小，越来越小哦。那越长电纳值越小。当它的长度为 0.25 个 lambda 的时候，它的电纳值会多少？0，因为跑到对面去了。然后它要是比 0.25 个 lambda 还要再来的大一点的时候，它的电纳值就会变正的了，开始变正的，因为继续绕嘛，绕上去所以电纳值在这一段是比较大的负值。我这样讲有没有对？你知道我意思啦负的比较多的比较大的负值。那到这一段第三象限的话是大小小于1的负值大概其实这个 button 它的最底部是-1啦，电纳值是-1，再来是-0.8、负0.6，所以第三象限是大小小于1的负值。第二象限呢，大小小于1的正值。第一象限呢，大小大于1的正值。所以 short stop 或者 open stop 其实正的负的电纳值都可以提供接近0的到接近无限大也可以提供。所以你才会看到这张图上面它会画那个 C 点的那个往下的 F 点，这个点对应的这一个点，不是应该是说它会画一条线从这边过来。这边过来的时候它所对应的那个电纳值是负 1.16。那你在 C 点的时候看到的导纳值是1加 1.16 J 1加 J 1.16， 但是下面这一条线呢，负 1.16 它对应到的是1点，所以这项艺术，这意思就是说你的那个 shortstop 的长度，假如从这里开始长到这么长的时候呢，它所看到的电纳值是负 1.16 J。所以你把一个这么长的 shortstop 跟那个原来的主干道做并联的时候，它所看到的导纳就会变成1加 1.66 J 减去 1.16 J 等于1。 好，那我们知道一这个位置是重要的，它可以提供负 1.16J。请问你的 show stop 的长度是多少？相对的注意啊，你把它拉到外面，它是0.363兰达嘛。但是注意啊，你起点不是0哦，你起点是0.25兰达，在右边嘛所以真实需要的 show stop 的长度是多少？0.113兰达。所以 again， 第四象限是负的大于1，负的 magnitude 大于1的；第三象限是负的 magnitude 小于1的；第二象限是正的 magnitude 小于1的；第一象限是正的 magnitude 大于1的。但是因为你是从4312这样转，所以你的长度0到0.125个兰达是右下角第四象限，0.125到0.25个兰达是第三象限，然后0.25到0.375是左上，0.375到0.5的话是右上，那反过来，假如说，我用 open stop 做可不可以？可以啊，但 open stop 的起点在哪里？在这边嘛，所以同样要达到负 1.16J 的电纳值，我 open stop 又要多长？0.363，比较长，对于传输线系统来讲，长不一定好，但也不一定说短就一定好，也没有这样的事啦。通常短一点的话，就表示说你那个电路的尺寸可以小一点，但真实的微波工程设计上面有一些其他的考量，所以不一定说长的就比较不好，短的就比较好。那另外也因为真实的微波电路工程上面的一些考量，我们等一下还会讲另外一个 matching 的方法，叫 double stop matching。那顾名思义，你需要2个 stop 在 double stop matching 里头，这里头是 single stop matching 只要1个，那听起来不是1个比较好吗？那为什么要1个？而且你发现single stop matching 一定有解，一定有解。double stop matching 还有所谓的无解区，double stop matching 大部分的问题大部分的 matching 可以解，但是不是所有都一定有解但是在实务上，你说真实的电路设计上 ，double stop matching 比 single stop matching popular。为什么？当然了，我们现在才学到这里，还不知道为什么。当然有时间的话，老师会讲一下。在工程上面的时候，为什么 double stop matching 反而比 single stop matching 常用、好用？原因是，应该这样讲啦，原因是 single stop matching 你要去调哪些东西？你要去调你那个插入 stop 的位置嘛，还有 stop 的长度，所以变成说你每次要换一个 loading 换一个负载的时候，你就要重新设计一次你的 single stop matching。但对于 double stop matching，它有一些特点，我们等一下会讲，它的结构比较固定，所以它变成说每次要改设计的时候，而且注意那个 stop 并联的那个 stop 提供的是什么？提供的是一个电感或一个电容嘛，它提供一个电纳值，那电纳值当然有正有负，它等于等效可以用电感或电容来提供。所以意思就是什么？意思是说我可不可以不要用 stop line， 不要用 transmission line， 我直接接一颗电感或接一颗电容？当然是对啊，可以啊。所以你要去做 single stop matching， 你只要在并联的地方加一颗电容或加一颗电感，也蛮也塞啊，也可以啊。所以真正在实务上，你常常看到所谓的 single stop matching， 它是用电感，用一颗一颗小颗，我们叫什么 SMD 嘛，Service Mount Device SMD 的电感或 SMD 的电容，来去把那个传输线的 matching 来完成。有在实物上常看到，好。但是真正用传输线把它拉出去的设计也不少。为什么？你不用再跟人家买那一颗LAMP 元件啊。你说老师，可能LAMP 元件我在那个什么 DG Key 上面一颗才5块美分啊。那以后你工作的时候，老板你的小组长就会跟你说，5块美分也是钱啊。哦，你要是做100万的，那是多少呢？就5万块啦。哦，所以有的时候你反正那个板子就在那边嘛，洗板子那个勒就勒一勒哦，你把它直接勒出来，就不用再焊那一颗啊，对不对？可以帮公司省5分钱啊，100万个就是5万块啊，对不对？哦，也是有的啦，所以，实物上面的考量还蛮多的。好，不过以这个例子来讲，你会看到从 B 点绕到 C 点所需要的距离是0.0415个 lambda， 而到了 C 点之后，它的导纳值是1加上 1.16 J。然后你要把那个 1.16 J 抵消的话，你就要用 show stop 或 open stop 提供一个负 1.16 J。所以只要 show stop 的话呢，你就要从你的那个 show stop 的长度就要从 D 转到1，所以它的长度会是 0.363 减 0.25， 可以吗？So as you can see from here, the imaginary part viewed from point C should be cancelled by connecting a short-stopping shunt. The required susceptance is minus 1.16. So the next question is how to create a short circuit stop with an input impedance of minus 1.16 susceptance. So again, we will use the Smith chart and looking on the ticks and values to create a short stop that provides minus 1.16 susceptance. And it's equivalent to move from point D to point E, which is located on the outermost circle of the Smith chart. So the short stop length required will be the difference between 0.363 and 0.25. So the distance, the length required for the short stop is 0.113 lambda. And the input impedance of this short stop is equivalent to 1 minus 1.16 J. So by connecting the transmission line and the shunt stop and the stopping shunt, the input admittance will move from point C to the center. Will move from point C to the center. So once you do the connection, you will jump from C to O. And on this plot, you see there is another solution that can provide you an intersection with the unit conductance circle. That is location F. So the length required to move from B to F will be what? The difference of 0.3335 and 0.125. So the length required is 0.2085 wavelengths. And at the position F, its admittance is 1 minus J 1.16. Therefore, to move from point F to O, you will need to connect in shunt with a stop that provides a susceptance of positive 1.16. So if you want to use that with a short stop, then the length required by the short stop will be equivalent to moving from point D all the way up to point G. And the length will equal to 0.25 plus 0.137. So the required length for the short stub will be 0.387. So for this solution, you will have the shunt stub location will be nearly 0.2 wavelengths, and the stub length will be approximately 0.38 of a wavelength. So comparing to the solution required by point C, the circuit size will be larger for point F. So so considering the circuit size, you may prefer solution of point C rather than solution of point F. Okay. And now let's try to play with the, okay, the next example, example 7.6, is the so-called double stub matching. So we will, again, using the Smith chart tool to perform double stub matching. As the name suggests, in the double stub matching design, you will have two short stubs. And for the two short stub design, okay, again, the background is the same. You have a 50 ohm transmission line system. The low impedance is 30 minus 40J. And here are two fixed conditions for the general two stub design. For double stub matching design, you have more degree of freedom in choosing the configuration of your transmission line system. But for commonly seen double stub matching design, the first stub is connected right at the termination. Right at the termination. And the second stub is connected at a fixed distance, which is 3/8 of a wavelength, 3个 lambda, 0.375 lambda, 3个 lambda. So at 3/8 of a wavelength away from the termination, you will connect the second stub. So the only design parameters to be determined will be the length of the first stub and the length of the second stub, while the stub location are already determined. So here you have L1 and L2. So what is the purpose of changing L1 and L2? To provide different values of susceptance, so that you can eventually reach matching condition, reach the origin. So with the reference of notation of the, well, so here's the configuration of the circuit. So the first criterion, first constraint is D1 equal to 0. So you are placing the first stub right at the termination. The second constraint is the distance between first and second stub is 0.375. And the consequence is, well, pretty much the same as the single stub matching. What is the input admittance view at this point 1 right 在这里头你要看到的导纳值是多少？就1啊。你希望看到在这里看到，在这条虚线的左边，你希望看到是1嘛，对不对？那在这条虚线的右边，你要看到的导纳值是什么？1减 JB2。好，因为第二条线 JB2 这条第二个 stop 能够给你的就是一个 JB2 的值。所以在虚线的右边，跟那个 single star matching 的那个问题是一样的。好，它在这里头，在虚线的右边，它必须要在 unit conductance circle 上面。好，所以在虚线的第二条虚线的右边，你希望它在这个蓝色的圈圈上面，然后透过第二个 stub 提供一个 B2 值，啊，加上去之后，你就移动到圆心了嘛，这样 matching 就做好了 ，OK， 好，所以第二条虚线，在第二条虚线的时候，你只要在蓝圈圈上就 OK， 好，所以下一步，或者再往前回推一步，就是 D12 为什么选择在 0.375 lambda 嘞？我们想想看，在 Smith chart 上面，你只要转 0.5 个 lambda， 你会转到哪里？转回原来的地方。转 0.25 个 lambda 会转到哪里？转到对面。那 0.375 嘞，3/4圈。好，所以那个 0.375 lambda 给你，意思就是说，你就是会转3/4圈。所以我们这边画的红圈圈哈。在 double star matching 的设计上面，它有一个特别的名字，叫做 auxiliary circle， 辅助圈。有没有看过这个字 auxiliary？ 那个小朋友骑脚踏车的时候，哈，或者你小时候骑脚踏车的时候，一开始是骑双轮的吗？不是嘛，4轮的嘛，旁边还有2个 auxiliary wheel 啊。所以那个红圈圈叫做 auxiliary circle， 辅助圈。它意思是什么？它把那个蓝圈圈转3/4圈。转过去，好，你只要转 0.5 个 lambda 的话，就是回到原来；转 0.375 个 lambda 就转到红圈。所以我第一个 stop 的目的是什么？到红圈。好，我在那个 load 的位置，马上就接一个 stop， 接那个 stop 的目的是要到红圈，因为你只要到了红圈，这里。接完 stop 之后到红圈，那么经过 0.375， 它就会到蓝圈，到蓝圈问题就解决了嘛。好，最后用第二个 stop 把它调回去。所以你从 Smith chart 上面来看，哈，其实 double star matching 不难。好，所以我会建议各位先在 example 7.6 里头把 double star matching 的原理搞清楚。那我们再回去7.3去看那个 double star matching 的那个数学式子，看起来很吓人啊，好，看起来很吓人。但你用 Smith chart 做的话，其实不难，好，所以红圈圈名字叫做那个，注意一下，蓝圈到红圈是顺时针转还是逆时针转？逆时针啊，好，好。蓝圈圈是在第二条虚线嘛，红圈圈是从第二条虚线倒推回去第一条虚线，所以它其实是 toward the load，not toward the generator， 所以它的那个转法是逆时针转的，所以这一点会转到哪里？注意啊，你这边再考验一下你自己。这一点是转到这里吗？还是转到这里？这里才对啊，这样才它要转3/4圈哦，好，所以这一点呢，转3/4圈到这里，好，这一点呢，转到差不多在这里，好。Okay, so the blue circle, the unit conductance circle, it stands for the the conductance you should have at the Y2 prime. Now, the real power of Y2 prime. And if we looking backward, move toward the load, then the locus formed by the unit conductance circle shall rotate 3/4 of a circle into the red one. So that should be the admittance mu from the left-hand side of the first stop. So the purpose of the first stop is adjust the susceptance so that it can make intersection with the red circle. Now I will ask you an advanced question. Do we have solution for all reflection coefficients on the Smith chart using the double stop matching technique? Well, the answer is no, because I already told you why. Yeah, because by connecting the short stop, you can only adjust the susceptance. You can only adjust the substance, which means you can only move on the constant conductance circle. You can only move on the constant conductance circles. If your conductance is a small number, you will have a larger circle, and it's bound to have an intersection with the auxiliary circle. If you have a large conductance, which will be located in this region, it may not have an intersection with the auxiliary circle. To be exact, the criteria is if G is greater than 2. If G is equal to 2, it will only have one intersection around here. If G is greater than 2, it will have no intersection with the auxiliary circle. So you will have no answer. So this region, which has a G value greater than 2, is referred as the forbidden region, like this. 所以从他没有讲 forbidden region. Okay. Yeah. For G greater than 2 is referred as the forbidden region. 听起来充满想象的一个名词。OK 那怎么办？假如你的 G 比2大怎么办？你用 single star matching， 或者是你换一下，其实有了，他们就说，那就把你那个 double star matching 的条件稍微换一下，比如说那个 double star matching 的那个起始位置不要是 D1 等于0，你把 D1 改成 0.125， 那个 circle 就会转过来了，就会再多转个 0.125， 所以。但你转个你 D1 要是设成 0.125 让打，你会有新的 forbidden region OK， 所以 double star matching 不是一定有解，但是你可以看到它没有解的范围其实是已知的啦，所以也不是那么难处理那好处就在于说因为 double star matching 的话 ，D1 跟 D2 是决定的。D1 跟 D12 是决定，所以你只要改变这2根的长度。假如你不是用真实的 transmission line 去做的话，你不用重新。假如你不是用真实的 transmission line， 而是用那个 SMD 的那个电感电容，我们知道那种东西它有不同的电感值、电容值嘛，所以假如你是用电感电容来去提供那个 susceptance 的话。那你只要换那颗电容元件或电感元件，换一个不同值的，你就可以重新做到匹配了嘛。所以它在实物上面有可能是比较方便的。假如你是一个公版的设计，那你可以说反正你就看看你的那个负载到底是多少，你调一下你的那个 short star matching 的double star matching 的那个 这两个的那个电容电感值，就可以达到 matching 的一个状态了嘛。好吧，我们今天我们 double stack matching 没有讲完了哈，下礼拜